CIRES. I'm an oceanographer. I do mainly computer modeling as my research topic. And Susan and Mark have kind of directed me towards some things that I hope are going to be useful for you guys to think about. I do all kinds of modeling from very small scale phenomenon like 1 meter scale stuff up to global climate models that have atmospheres and oceans and ice and all of that stuff. And so I wanted to try and talk a little bit about how how hard it is to understand those things on the large scale and how they get to a more human size problem, how you get from the global scale down to the size of something we care about, like is it going to rain in a couple minutes or not? And that sort of thing. And hopefully you'll see what some of the challenges are. And in particular, I'm going to discuss two, I guess, examples of the kinds of thinking that you have to use to get from the large scale down to the small scale to understand what really sets regional climate or what really sets climate temporal variability. So, and please stop me if there are any questions, which I hope there will be. So what is climate? Well, first of all, how does climate differ from weather? Any guesses?
We've talked about this several times.
How many
Good.
sweaters are in your closet versus if you're going to wear a sweater today? I like that.
That's a good one. That's a very good one. Okay, so it's a question of time scale, thinking of it from the physics point of view. And why does climate vary regionally? Why? Well, because in different places, there are different components of the climate system that are playing different roles, and also different places have different forcing. We'll get into what that means in a little bit. Why does climate vary temporally? So regionally, now temporally. Well, just like in the regional case, you can have different forcing at different time periods. So the sun gets brighter, the sun gets dimmer, that kind of thing. There are also slow oscillations in components of the system that can be sort of rung like a bell and resonate with this changing forcing. And then there are also very obscure things like chaotic nonlinear interactions, which I probably won't talk much about. But so, does this kind of variability affect the systems and our response to climate change? Well, certainly. Okay, so this is the little cartoon of the climate system. We have the sun shining down, we have atmosphere, we have Earth. Some of the radiation gets trapped in, some reflects back, some goes out as sort of as radiation coming off of the heat of the planet in a long wave radiation. And so without the climate system, and by climate system what I really mean are the ocean, ice, atmosphere, and the greenhouse gases that are in the atmosphere being an important part of the climate system, the Earth's temperature would be more like what it is in the moon, which is minus 184 centigrade to 100 centigrade. Instead, it's much closer to the limits set by the freezing point and boiling point of water, so around 90 C to 58 C. So the water, the greenhouse gases, the interaction of the climate system really stabilize the climate so that it's much, it's not as cold and as hot as it is on the moon. Okay, so who are the people? Well, so hopefully you guys have seen some of these people. So this is, so all of the modern research in climate change really got started in the 70s when this guy, Jules Charny, was set by the National Academy to do an assessment of what happens to climate. And they came up with the idea that with doubling CO2, you get a 1.5 degree to 4.5 degree warming. And how did they get that idea? Well, there were two modeling groups at the time, Suki Minami and Jim Hansen. And one group said 1.5 degrees, the other said 4.5 degrees, so 1.5 to 4.5 degrees was the guess. But even earlier, Svante Arrhenius had estimated that doubling CO2 would rise about the same amount. And he said 5 to 6 degrees Kelvin, and halving it would decrease it by 4 to 5 Kelvin. So these ideas have been around for a long time, and modeling of it has been around for a fairly long time too, since the 80s. Well, we're talking about regional, smaller scale stuff, not the whole climate system. So how do we get from the whole world, down to a regional scale? Well, in a model, it's kind of represented by how small your grid size is. And as the computers get faster, the grid size gets smaller and smaller and smaller. So you probably can't tell where that is. So this is the IPCC first assessment report, but there's some land and there's some ocean. It's not until you get down, maybe you can start recognizing where this is. So that's Europe. And so in the first IPCC report, as you get down to the bottom, then you can start to recognize. So obviously, if you're trying to predict the climate of somewhere like a regional climate variations of somewhere like Great Britain, when Great Britain it doesn't even appear as an island in the low resolution model, it's going to be hard to do that. Okay? Well, so here we go. So a nice way in which you can think about how climate works is the example of maritime versus continental climate. And the key idea here is that water has a really large heat capacity. So if you put a lot of energy into water, its temperature doesn't change very much. Put the same amount of energy into air, its temperature changes quite a lot. So what do I mean by that? Well, here's a map of the day to night temperature change all around the world. And white colors here is almost no change from day to night temperature, and red colors are lots of change from day to night. And you can see that all the places where there's water don't change temperature very much between the day, but where we are is one of the pretty red places, and deserts, and high altitude deserts where it's very dry and there's very little moisture in the air, are very, very red. Places like Australia, also very red and very dry. So regional climate, in this case, is really being affected by how much water there is. Is there water near you? Is there water in the air? How does that work? So that's the essential idea. And so you get only about 34 degrees variation over the open ocean, but you get peaks in different locations that are much, much colder, much, much hotter than those relatively stabilized temperatures. And this is just a different way of saying it. I'm going to skip this for interest of time. So here is the time series of over the year how the temperature changes in two different cities in the US. One of them is Norfolk and one of them is San Francisco. So San Francisco is the one in green and Norfolk is the one in blue. And you can see that San Francisco's temperature doesn't change as much over the course of the year as Norfolk's does. Now they're about the same distance from the coast, so what's the difference? Any guesses? Ocean currents could be one possibility. What else? Prevailing winds, another good one. And that here is really a big part of the story because the wind is blowing from the west to the east. So you get a sea breeze all of the time in San Francisco, whereas in Norfolk, you don't get a sea breeze that often. Well, sometimes you do, sometimes you don't. But the seasonal variation is much larger because they're getting breeze of dry air rather than moist air. Okay, so there we go. Which way does the wind blow? Well, all right, so that's our story about different components because some places, different components are playing a bigger role. Like some places have ocean, other places don't. That's one very simple example of different components controlling regional climate. What about different forcing? Well, we know that the equator is hotter than the poles. And we know, and why is that? Because that's where the sun is shining more directly, more of the year. And there's this band, that the Earth's not perfectly straight up, it's tilted over. So we have seasons as things move around. But, so the idea is that another way of understanding what the climate system does or why it's moving, why it's doing all this stuff, is that you're heating the equator a lot and you're cooling off the poles. So you get excess heat at the equator, excess cooling at the poles. So how does that work? Ocean moves stuff around, moves heat around. The atmosphere also moves heat around. One of the powerful ways where we are in the extratropics that the atmosphere moves heat around is by storms. Because storms take warm, moist air from the tropics, carried up to the pole, take cold polar air down, and when you get a cold air outbreak here, it's usually that kind, which is, you get a big burst of cold air, because it's trying to move hot and cold to balance out that temperature difference, to balance out that heating difference between the hot equator and the cold poles. So in a sense, most components of the climate system, you can just think of them as trying to take the excess heat from the equator and get it out to the poles. That's a big part of what the system is doing. So that obviously leads to changes in regional climate because some regions are getting heated and some are getting not heated, and other regions are in, like we are here, are kind of in the zone where the heat is trying to get passed over us. So we get a lot of storms, we get a lot of snowstorms, we get a lot of stuff rearranging itself in order to get that heat to pass over our head. And it's exactly the same in the ocean. There you think of things like the Gulf Stream carrying big warm water toward the north and warming up Europe, that kind of thing. So those, not only can there be different components locally, but you could kind of play a different role in this larger system of uneven heating, depending on where you are. So that's another way to understand kind of what causes these regional variations. And now I have a very quick slide with a few other kinds of regional variations that we climate scientists think about a lot. Things like monsoons, which have to do with seasonal reversals of the wind. And so you get a big rainy season part of the year, you get a dry season the other part of the year, you get either sea breezes or breezes coming off of land, depending on the time of year. And that has a lot to do with where the places that have monsoons are located in relation to the larger climate system. They're sort of near the edge of that tropical zone. So sometimes they're kind of connecting to the tropics, and sometimes they're sort of distant from the tropics, depending on which way the wind is blowing. Something that's really important here are orographic effects, which means essentially when the air has to go up to get over something, it likes to rain. When it has just gone over something, it has already rained, and so it's usually dry. So here, when we get a big snowstorm, it's usually an upslope wind. We get wind blowing up the mountains, and as it goes up, it wants to dump all its moisture, and it dumps it on top of us. But our prevailing winds come over the mountains, so we have very dry climate. We're in the rain shadow of the mountains. Because when it's coming that way, it's already dumped its moisture before it gets to us. So it's hot, dry air coming down from above. They also like to go around. It gets very complicated when you really think about how that all works. But those kind of things can affect regional climate very much. So much so that even in places like Boston, which you think of as being relatively flat, the major difference between which neighborhoods in Boston get how much snow is whether they're on a hill, on a slope, or in a valley. Even in a flat place, that can still be the controlling regional variation in how much snow you get. So here, it's very complicated when you think about the snow, and you know, some of the mountains have a lot of snow, and they also have a lot of ski resorts on them for the same reason. And that is a very spot by spot, just exactly the shape of the mountains that controls that effect. And we'll talk about how to skip over these other things. All right, so that's why that's why you get regional variations, because sometimes you have different components playing a different role, and sometimes you have different forcing by latitude or by season. So what about temporal variations? So in my mathematical eye, I think of those as being very similar things. You know, you just have what's your independent variable? Is it x or is it t? But in fact, in the physical perspective, the time variation problem is quite different from the spatial variation problem, because the things that cause changes in time are much more tricky to think about. They are more like masses on springs kinds of things. So you guys know when you have a mass on a spring, and I was going to bring a slinky, but I've forgotten my slinky. Actually, I do have a slinky back there, but anyway, I can explain it better. So you can imagine if you have a pendulum or a mass on a spring, or a kid on a swing set is maybe the easiest one. If you push at the same frequency as the swing, you get a very big response. So every time it comes back, you give it a push, and the swing goes higher and higher when you're doing that. And now if you can imagine, this is a very hard thing to do because it's so unintuitive. If you push at a random time that has nothing to do with the period of the swing, they just kind of fall around and they don't go anywhere, and it doesn't build up any momentum. So that kind of effect, which physicists call resonance, when you are forcing near the frequency that the natural oscillation would have underneath, tends to get a very large response. So a lot of the things that we call climate oscillations in time are really resonating with slow physics in typically the ocean or sometimes the ice. And then there's also chaotic nonlinear interactions, which again I'll say very little about except to say that it's there. So if we look, this is a great paper by a friend of mine, and it has this thing. So this is a power spectrum, which tells you how much variability there is at different periods. So this big spike, this really tall spike that you see, that's the 1 year. So the seasonal cycle is there. It's a lot of power. There's a lot of variability at 1 year period. And then as you go to longer and longer times, you see that there's just sort of more and more power hiding up there under this big hump, and it drops off almost with those straight lines, but with lots of wiggles. And this is a very complicated thing to do because this goes back a million years. So there are 1 million year timescales down to weeks on the other end. And you can see that there's all kinds of stuff happening at all of those periods. So in the beginning, we said climate was things that were slow. So where's slow? Well, slow is everything on that side of the big spike, everything to the left-hand side of the big spike. So how do you explain that? Well, there are no swing set periods that are popping up, obviously. There are no big humps where something is kind of being resonantly forced. So this is why the chaotic nonlinear interaction part of it is chaotic nonlinear interactions would give you things like those straight lines. But maybe there are a few humps there, here and there. And you can see a few, and we know a couple of them. So I want to talk about one of them in particular that does have kind of a hump if you get in there close. It's a hump at the near 4 to 6 year range, and that's El Nino. So El Nino switches on and off. It goes from warm Pacific sea surface temperatures, and this is actually the power in Pacific sea surface temperatures that we're looking at from different paleo proxies. So it wobbles. So sometimes the tropical Pacific is extra warm, and when it does that, there's a connected wind, and it moves the rainfall from one part of the Pacific to a different part of the Pacific. And so it changes the regional climate. But it actually is such a huge signal that it changes the global climate because it moves that rain, it moves those winds, and then those signals propagate out all over the world. And so there are detectable other things connected to this wobble in Pacific sea surface temperatures. So it's kind of a funny thing, but it really, so we'll try and get to it. So here's I guess this is talking about the swing set case. So where might we find swing sets that have climate timescales to resonate? Well, the atmosphere is really fast. In fact, the atmosphere forgets almost everything in less than 2 weeks, which is why it's hard to predict the weather more than a week ahead. So it has very little resonance on its own with climate timescales. But now the ocean has lots of slow things. There are waves. There's waves which take 4 years-ish in the El Nino case. There are gyres, things like the part that carries the Gulf Stream north. That's usually tens of years periods. There's the meridional overturning circulation, another part of the Gulf Stream, the thing that in the day after tomorrow was supposed to shut down and cause great havoc. And that has a thousands of years time scale. And then the cryosphere has hundreds to thousands or 10,000 year timescales in it as well. And so things like ice ages come and go on these tens of thousands of year timescale. And it's a resonance between very small changes in the solar forcing and the things that ice likes to do on those timescales, like form ice sheets and then take them away. Okay? So here's El Nino and La Nina on the left-hand side, El Nino on the right-hand side, and this is showing that the rainfall has moved out to the middle of the Pacific during El Nino instead of being far on the western side of the Pacific in La Nina. And you can see the sea surface temperature, which is colored. There's more warm sea surface temperature in El Nino and less during La Nina. And that's related to the fact that the thermocline, which is basically the region where the warm surface water changes to the cold abyssal water, is more tilted from east to west in one case, the La Nina case, and less tilted in the El Nino case. And so this is something, so you can imagine there are waves running around, and when these waves are running back and forth on the thermocline and tilting it, wobbling it back and forth, when they hit it just right, the thermocline tilts, the wind changes, the precipitation changes, and once it gets stuck over there, it's happy there for a little while, for a season or two. And then it flops back down when those waves run away and go do something else. So it's really what sets the time scale for switching from El Nino to La Nina is the fact that those waves take a couple of years around the time scale between an El Nino and the next one to ring around and run around back and forth across the ocean. And these are a special kind of waves, very big waves, yeah?
Has the time period changed between El Nino and La Nina switches over the years? Has it become more frequent?
It has, things have changed. This is things have changed. So we have very good records of El Nino since the 80s. We have moorings out all across the Pacific measuring everything that's going on. We have okay records going back till about World War II. And we have pretty poor records going back before that. But nonetheless, people have tried to reconstruct this and see how it's changed. The problem is if it only comes every 4 years, you really need a long time series before you see enough events to tell them apart. And so it looks like now El Ninos are, we've had a couple of really strong ones, one in 82 and one in 97 recently. And in the 50s, it looked like there were more La Ninas. But it's very hard to tell because the record's not really long enough what that's connected to or whether that's just what it does. Maybe it just wobbles around like that, or maybe it is actually a consequence of climate change. We're not sure. Does that sort of answer the question? Okay. And so here are some of those waves. So this is just in that red line, this is showing the sea surface temperature, and you can see that there are blobs of warm stuff zooming down leg one from east to west, which are called Rossby waves. Then they reflect at part two, and then they zoom back the other way in a way called Kelvin waves. And so you can see basically that the blobs of red are continuous. So you can see those waves carrying the sea surface temperature pattern around in that loop. And why they go from east to west and why they go from west to east is a fun story, but not for today. Okay. Oh. So I was going to show you a movie of the onset of the 97-98 El Nino, but I don't think it's going to work in this format. Okay, so here's what El Nino does to the rest of the world. And this is another way in which you could have regional climate. You might sense more or less El Nino depending on where you are. And so this is a map of places that have been connected to El Nino. So when you get a big El Nino, you tend to get warm in the red spots, cold in the blue spots, wet in the green spots, dry in the brown spots. And so you can see that the local effect of that dry ring and the wet and warm ring in the central Pacific is not the only thing that goes on. There's stuff all the way around the world, all the way down to Australia, all the way up to Alaska, as far away as Africa, all the way around the world. And it's really because once you get this motion going, once you get locked into an El Nino or a La Nina, it changes the weather all over the world by slightly shifting all of those regional climates around, by putting more moisture in the air, taking more moisture out of the air, changing the path of the jet stream, that kind of thing. Okay, so now to the more pressing question, does El Nino affect snowfall in Colorado and whether it affects the ski season, which is what everyone always wants to know? And it's actually a very tricky thing to figure out because of this orographic effect, because of this regional variations between some hilltops feeling things and other hilltops not feeling things. That is a much bigger effect. So depending on where you look, you can maybe find connections and maybe not. And so this is a big table basically to tell you that it's very hard in at least climax Colorado to make a clean connection between El Nino years and good snowfall or El Nino years and bad snowfall. And in Boulder, January precipitation during El Nino, the average is 0.45 inches. And during La Nina, the average is 0.72 inches. But that's not the variation between 0.45 and 0.72 we get every year anyway. That's not, if you just plotted January, it would look like this. And then that little bar would be just a tiny fraction. So it's not even clear whether that's a statistical anomaly or whether that really is something there. So what's it going to be like this year? This is one of the things that you might want to know. Well, so El Nino, at the moment, we're coming out of an El Nino, and there is a La Nina watch. So why can we predict this far out? I mean, El Nino doesn't really, or La Nina doesn't really get fired up until around December. Why do we know now? We have a hard time predicting. I mean, it was supposed to be sunny today, a week ago. So how do we get from where we can't predict the weather a week out? How can we predict the climate system almost a year out? Any guesses?
Ocean temperatures over the
Exactly. So you're seeing those waves, those slow waves. Once you start to see them developing and starting to propagate those slow waves around, it's not really a weather problem anymore. It's become a problem of just predicting the slow time scales of the ocean. And those turn out to be predictable for a much longer horizon than the really fast time scales of the atmosphere, which has a lot to do with the fact that the ocean holds more heat for the same temperature change as we talked about at the beginning. All right, so now one brief word on chaos and nonlinearity. When you push a swing set, it's essentially a linear system. It responds like a linear oscillator, and what that means is that in the equation for it, the simple equation for a pendulum, there's no dependence on how high you're pushing. And so there's no amplitude effect, and also another consequence of it being a linear system is that all the frequencies are independent. So if you force at one frequency, you get a response at that same frequency. If that frequency happens to match the natural frequency, you get swinging. If it doesn't match, you don't get much. You just kind of get random wobbles, right? A nonlinear system, and in particular a chaotic nonlinear system, which we know the atmosphere and ocean and the climate system to be, that's not true anymore. Because in those kind of systems, which actually are the more common systems in the real world, most systems are nonlinear. The linear systems that we study in physics are the reduction of the real world to the simplest case where we might understand. In a nonlinear system, different frequencies can talk to each other. So I might force the seasonal cycle every year by our orbit around the sun, but in fact, that forcing the seasonal cycle can sensibly affect El Nino, even though the time scale is 4 times longer. So different frequencies can talk to each other, but only when it's a nonlinear system. And so we know that it's a nonlinear system, and I won't tell you anything more about it except you can get simple ideas from thinking about simple concepts, but really to kind of integrate all of our knowledge about how this stuff works, we kind of have to resort to using computers and modeling the whole system all at once. And that gives us at least a shot at getting this kind of response right, whereas doing it with pencil and paper gets a little hard when you start thinking about systems like this. And people have known that. That's why physicists don't study this kind of system as the simple case, because you can't do it on pencil and paper, or you can't do much. So to conclude, I guess, so the basic forcing in the climate system is pretty well understood. Arrhenius had it more or less right about 100 years ago. It has global warming in there, it has CO2 in there, has the effects of water vapor and heat capacity are all in there. And the water's heat capacity plays a large role, not only in the whole Earth, moisture in the air trapping heat in, water vapor is a big greenhouse gas, but also in distinguishing different regions' climate from one from the other. How much water you got in the air makes a big difference, and how close you are to the ocean also makes a big difference. So this and the other variations in the relative roles of different climate components, like do you have ice or not, leads to large regional and temporal variability of climate. And the complexity is really big. So it's a very complicated thing to do. And I say this because I'm a modeler, and modelers like to think that models are the only way ahead, but this really is a system where it's very hard to imagine that once you get beyond this sort of simple idea, these kind of basic concepts like, are you close to the ocean, are you far from the ocean, how much heat capacity do you have because of the moisture in the air, once you get to thinking about the way the system really works and all of the interacting pieces and how far the effect of El Nino extends around the Earth, it's very hard to do that in the absence of computers. So you can do that with computers, and you can look in data, and you can hope that the stories match, and the better they match, the better we understand the system, and they're matching better and better, but we still have a long way to go. So there you go.